Now that we've had a chance to look at the titration curves for strong acid and strong base titrations, we're going to look at the differences in our titration curves when we have a weak acid with a strong base or a weak base with a strong acid. Let's start by examining the difference between our strong acid, strong base curve and a weak acid, strong base curve. So in a strong acid, strong base titration, where your strong acid would be your titrand, so it would be in the flask, we see that our pH starts lower for strong acid. We have that gradual increase in the pH until it gets to the equivalence point. We have a sharp increase in pH at the equivalence point, and then there is a gradual increase after the equivalence point, ending at high pH, which is characteristic of the strong base. In your weak acid strong base titration, the pH of your starting solution, your weak acid, is going to be higher. So note the difference there. We have a gradual increase as we add our strong base, and this increase occurs in what we're going to refer to as the buffer region, and we'll learn more about that in a little bit. Then we're going to have the steep interval at our equivalence point, and beyond our equivalence point, we notice that it's very similar in shape to our strong acid, strong base titration curve. So note the difference in the shape of the curve, and note also that this steep interval at the equivalence point is less pronounced when we have a weak acid, strong base titration curve. Similar to what we did with our strong acid and strong base titration curves, we're going to look at the approaches to calculating the pH at different points along the titration curve. We're going to look at before the titration starts, so when no titrant has been added and the flask only contains your weak acid solution, up to this equivalence point, and we're going to look at the fact that this is referred to as your buffer region. So this solution will now consist of a series of buffers. We're going to look at the pH at the equivalence point and note the differences to our strong acid, strong base titration. And then after the equivalence point, what happens when we have an excess of the titrant in the solution and how that interferes with the pH of the solution. So again, just to look at the points along the curve that we're going to take a look at, we have at the initial point up to when we're getting to the equivalence point, at the equivalence point, and then beyond that equivalence point. As a reminder, in most of our titration reactions in the laboratory setting, we would be monitoring the pH of the solution as we go through at different points in the titration reaction. Today, we're going to look at an example where we know the concentrations of the acid and base involved, and we are going to make some calculations about what the expected pH would be at different points in the reaction. So this example, we are asked to plot the titration curve for the titration of 20 cm cubed of 0.105 molar acetic acid with 0.083 molar sodium hydroxide. So acetic acid or organic acid is a weak acid and sodium hydroxide is a strong base. So the equation associated with the dissociation of your acetic acid in water, as we can see here, produces acetate ions and hydronium ions. Because your acetic acid is a weak acid, we know that it only partially dissociates and it has a constant, your acid dissociation constant associated with it. This acid dissociation constant, Ka, is equal to 1.75 times 10 to the minus 5, and the pKa of our acid found by doing minus log of your Ka is 4.76. So before the titration starts, our weak acid will partially dissociate and an equilibrium will be established in the flask. As we've seen before, your acetic acid dissociates in water to produce your acetate ions and your hydronium ions. And the concentration of acetate ions and hydronium ions will be equal because they both came from your acetic acid. Again, we see the Ka expression for your acetic acid. Now, when we are determining the hydronium ion concentration, we must determine it using the acid dissociation constant because it's a weak acid, so only partial dissociation is occurring. Therefore, we can make some adjustments to this K expression because we know the concentration of acetate ions and hydronium ions will be equal at this point in the reaction. We can make some adjustments to our Ka expression and solve for the hydronium ion concentration. Once we do this, this concentration of hydronium ions can be used to determine the pH. So pH being minus log of your hydronium ion concentration. And so we see that the pH should be 2.87 for this particular example. And I want you to notice, just as we discussed when we looked at the titration curve, that the initial pH is higher for a strong acid solution than it is for your weak acid. So in the strong acid example, we saw where your pH was somewhere around 0.95, and in this example, we have a pH of 2.87. So as our base is being added to our solution of our weak acid, we see that the pH starts to increase. So in this region of the titration, the solution is going to consist of a series of buffer solutions. And so we're going to examine how the pH changes up to this equivalence point for your titration. We need to know two things. We need to know what the equivalence volume is for our reaction, and we need to be able to calculate the pH of a buffer solution. So first, what is equivalence volume going to be? So for a titration reaction, we have acetic acid reacting with sodium hydroxide. Acetic acid is a monoprotic weak acid, and then sodium hydroxide is monobasic. So we have a one-to-one reaction between them. So at the equivalence point for our reaction, the number of moles of sodium hydroxide added will be equal to the number of moles of acetic acid that we originally had in the flask. First, we find the moles of acid, concentration times the volume in liters to give us the number of moles of our acid. And because there's a one-to-one reaction, it means we need an equal number of moles of base for our reaction. Our moles of base required to neutralize this amount of acid will be equal to the concentration of our sodium hydroxide times the volume. So, because we know the moles and we know the concentration of our sodium hydroxide, we can solve for the equivalence volume, which is determined to be 25.3 centimeters cubed. Now that we have a little bit more information about the equivalence volume for our reaction, we're going to take a quick look at buffer solutions. A buffer solution contains a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. Some examples include acetic acid mixed with sodium acetate, or ammonia mixed with ammonium chloride. And for example, in the laboratory setting, phosphate buffers are popularly used as buffers. Now, your buffers are used to keep the pH of a solution relatively constant. So if you have a solution whose pH does not change very much when small amounts of strong acid or base is added to it, this is referred to as a buffer. And the capacity of the buffer is a measure of how much acid or base would need to be added to it to change the pH by 1 unit. Where buffers are concerned, they are very critical to the proper functioning of our bodies. So the pH of our blood needs to be maintained at a constant level. And so, for example, there's a buffer solution in our blood, carbonic acid hydrogen carbonate buffer solution that helps to maintain the pH and is very important for proper functioning of our cells, as well as ensuring that we have optimal pH for enzymes in our body. So now that we know what the equivalence volume for our reaction is, which is 25.30 centimeters cubed of base needed to neutralize our acid. So let's look at what the pH would be like up to the equivalence point. So as the base is being added, we have the reaction of our acid plus base to produce acetate ions in the solution and water, right? Acid plus base giving us salt plus water. This is a one-to-one reaction. So we're directly producing acetate ions in the solution when your base reacts with your acetic acid. Now, when this happens, the equilibrium that we looked at before, the equilibrium between our acetic acid and acetate ions, re-establishes itself in the flask. And so, in order to figure out what the concentration of our hydronium ions will be, we have to think about this equilibrium. Now, the hydronium ion concentration is going to be related to the Ka of your acid and the concentration of acetic acid in the solution and concentration of acetate ions that we have in the solution. So to calculate the pH, we need to know the hydronium ion concentration. And so in order to figure that out, we have to first have a better idea of what the concentration of your acetic acid would now be, right? Because we just used some of it. And what the concentration of your acetate ions would be since we just produced some of it. So as a reminder, initially we had 20 cm cubed of acetic acid in the flask, and we determined that the number of moles of acetic acid were 2.1 times 10 to the minus 3 moles. Let's look at a scenario. What would the pH of the solution be after we've added 5 cm cubed of our base? First, we want to figure out the number of moles of base that we've added, and we can determine this by the concentration of the base multiplied by the volume in liter, and that tells us that we've added 4.15 times 10 to the minus 4 moles. So we see that this number is less than the number of moles of acetic acid. So if you want to think about it as which one is the limiting reagent in this example, all right? Now the reaction is going to take place between our acetic acid and our hydroxide ions to produce acetate ions and water. A one-to-one reaction is taking place. So because we have 4.15 times 10 to the minus 4 moles of our base added, it will only use up 4.15 times 10 to the minus 4 moles of our acetic acid. And therefore, only 4.15 times 10 to the minus 4 moles of our acetate will have been produced from this reaction. So now that we've produced some acetate ions in the solution flask, the equilibrium between our acetic acid and our acetate ions will need to be re-established. So in order to determine what the concentration of hydronium ions would be in the solution at this point, we need to figure out what the concentration of acetic acid is now and what the concentration of acetate ions is as well. So first, the moles of your acetic acid remaining would be the difference between the initial number of moles minus the number of moles that were used up, and tells us that the number of moles remaining would be 1.69 times 10 to the minus 3. To figure out the concentration, we do the moles divided by the volume in liters, and this volume that we're using is the total volume that is now in the flask. It would be the 20 for the acid initially there, plus the 5 cm cubed of base that was added. So now, at this point, the concentration of your acetic acid is going to be moles divided by volume, which tells us that this is the concentration at this point. And we also figure out what the concentration of our acetate ions would be. Would be the moles of it that were generated. Recall, it was 4.15 times 10 to the minus 4 moles, also divided by the total volume of the solution, and this tells us what the concentration of acetate ions would now be in the solution. Let us first recall the K expression for acetic acid, and because we want to figure out what the hydronium ion concentration is in order to determine the pH, we can transpose this expression for hydronium ion concentration. At this point, we know what the Ka for acetic acid is, and we have the concentrations for acetic acid and also for acetate ions. So we plug in these values, and this helps us to determine what the hydronium ion concentration is. Once we have the hydronium ion concentration, we can use this to determine the pH by doing minus log of hydronium ion concentration, and pH is determined to be 4.15. So, one of the things to note, now as we said, once we reacted with our base, we produced acetate ions in solution, but we still had some acetic acid that was still remaining. Because your solution contains both your acetic acid and its conjugate base, your acetate ions, this solution is now being referred to as a buffer solution. And this is why we talk about the buffer region on the titration curve. Some of you may already be familiar with the Henderson-Hasselbalch equation. And so we're going to look at another way that we can determine the pH of a buffer solution. So remember, our hydronium ion concentration is also equal to the Ka times acetic acid concentration divided by acetate ion concentration. Now, if we take the log base 10 of both sides of the equation, we get this expression here. Log of hydronium ion concentration equals log of Ka plus the log of our acetic acid concentration divided by our acetate ion concentration. If we take the minus, putting a minus sign in front of each term is going to give us minus log of hydronium ion concentration equals minus log of Ka plus the log of, now notice these have switched, log of our acetate ion concentration divided by your acetic acid concentration. Now look at this. Minus log of hydronium ion concentration is equal to what? pH. And minus log of Ka is equal to pKa. So this now gives us pH is equal to pKa plus the log base 10 of the ratio of your acetate ion concentration divided by your acetic acid concentration. And when we're applying this to different systems, we can have it as conjugate base, a log of the conjugate base concentration divided by the acid concentration. This is a Henderson-Hasselbalch equation that can be used for the calculation of the pH of a buffer solution. And if you apply this equation to the example we just looked at, you should get the same result. So let's now look at another important point in your titration. And this is a point where your titrant volume is equal to half of the equivalence volume. And this is called the point of half neutralization, or the half titration point. And so at this point, the number of moles of the base that has been added would be equal to half the number of the moles of acid initially present. So if only half the number of the moles of acid have been used up, then it means that we've also produced an equal number of moles of conjugate base. So that means the concentration of the acid, your weak acid, and its conjugate base will be equal. So remember this expression, and because the concentration of acetic acid, for example, and the concentration of acetate ions would be equal at the half neutralization point, then it means that if we look at our K expression, it means that if the ratio between this and this would be 1 to 1 because they're equal, Ka would be equal to the hydronium ion concentration. And based on the Henderson-Hasselbalch equation, right, because they are equal, that goes to 1. So pH would be equal to pKa. So when you're examining your titration curve, when you look at the half neutralization point in a weak acid strong base titration, you expect that the pH at the half neutralization point is going to be equal to the pKa of the acid. So we're now at the equivalence point in our weak acid strong base titration. And unlike our strong acid, strong base titration, the pH is not going to be 7. So let's take a look. Now, remember, acetic acid is reacting with your base to produce acetate ions and water. At your equivalence volume, all of the acetic acid is going to be neutralized, and you would have produced the 2.1 times 10 to the minus 3 moles of acetate ion at this point, right? So the conjugate base. Now, this conjugate base is going to hydrolyze. It is also going to hydrolyze in water to produce hydroxide ions and acetic acid. So it is a weak base and it's going to behave like this in water. Now, what this means is that it establishes a new equilibrium in the flask, and this equilibrium is described by the base dissociation constant for your acetate ion, and it would look like this. So we're at the equivalence point in our reaction, and if you recall the relationship between the Ka of your weak acid and the Kb of its conjugate base, Ka multiplied by Kb equals Kw. So that provides an easy way for us to determine what the Kb of your acetate ion would be. Now, recall the expression for the Kb of your acetate ion, and we can determine it, this Kb, by 1 times 10 to the minus 4, which is your 14, which is your Kw, divided by the Ka of acetic acid to give 5.71 times 10 to the minus 10. Now, once we produce acetate ions in solution, when the acetate ion hydrolyzes in water, it's going to produce equal concentrations of hydroxide ions and acetic acid, because there'd be a 1-to-1 stoichiometry between the two. Right? So it means we can rewrite this Kb expression as hydroxide ion squared, the concentration of your hydroxide ion squared being equal to the Kb multiplied by the concentration of your acetate ion. So Kb equals hydroxide ion squared divided by acetate ion can be written down here to give hydroxide ion concentration squared equals Kb times acetate ion concentration. First, we need to make sure we have the correct acetate ion concentration, which would have been the number of moles produced divided by the total volume in the solution. So the original 20 of the acid that was there plus the 25.3 of the base which was added. So remember, this is the equivalence volume. So the total solution volume at the equivalence point would be 20 plus 25.3, which would give us 45.3 centimeters cubed. So first we find the acetate ion concentration, and then we use this in our expression up here to find the hydroxide ion concentration to be 5.14 times 10 to the minus 6 moles per dm cubed. When we have the hydroxide ion concentration, remember, we can't find pH directly from the hydroxide ion concentration, but we can find the pOH, which is the minus log of the hydroxide ion concentration, and then pH is equal to 14 minus pOH to give us 8.71 as the pH of the solution at the equivalence point. So you'll notice whenever we have a weak acid, strong base titration, the pH at the equivalence point is going to be greater than 7. So it's going to be more basic in nature. So now, after the equivalence point, this is when we've added more base than we actually need to neutralize our acetic acid. For example, if our titrant volume is 25.8 centimeters cubed, first we can figure out the number of moles of hydroxide ions that were added beyond the equivalence point. And we can do this by doing concentration of our base multiplied by the volume that was actually added. And in this case, the additional volume would have been 25.8 minus 25.3. So that would be your additional volume of base added. When we do concentration times the volume in liters, it tells us that we've added an excess of 4.15 times 10 to the minus 5 moles of hydroxide ions. And we can now determine the concentration of hydroxide ions by doing the number of moles divided by the volume of the solution, the total volume of the solution in liters. Once we have the concentration of hydroxide ions, we can use this to determine the pOH of your solution by minus log of hydroxide ion concentration and therefore the pH, right? Which would be 14 minus your pOH to give you 10.96. Okay, so just as a summary, some of the things we need to do when we're trying to figure out the pH at different points in our titration curve, we need to know what the equivalence volume is. We should calculate the pH at when the titrant volume is equal to 0. So when we only have our weak acid, for example, in the flask, and we know we have to use the Ka expression for this because it's a weak acid. When we are calculating the pH before the equivalence point, this would be our buffer region. We can use our Henderson-Hasselbalch equation, or we can use our Ka expression again. At the equivalence point, what are we using? We have to be using the Kb expression because at the equivalence point, we've used up all the weak acid and produced its conjugate base, and its conjugate base is going to be hydrolyzing in solution. Beyond the equivalence point, when your titrant volume is greater than your equivalence volume, we need to be calculating the pH based on the excess base that is now in the solution. Right? And don't forget, at the half neutralization point or the half titration point, because we would have produced we'd have equal concentrations of the acid and its conjugate base, means the hydronium ion concentration is going to be equal to the Ka of the acid. And so the pH of your solution is going to be equal to the pKa. All right, so remember, for weak acid strong base titration, the initial pH is higher than for our strong acid strong base. We have a gradually rising portion in the buffer region. The pH at the equivalence point is going to be greater than 7, and the steep rise interval is less pronounced. Now, another thing I want to point out here is that we'll see an example. We have two different indicators here. We have methyl red and we have phenolphthalein. Remember, we said that we want to choose an indicator that is going to give us a result that most closely matches the equivalence point of our reaction. Now the question, would you use methyl red to indicate the endpoint of this reaction? No, because as you can see, methyl red is going to undergo that color change in the buffer region and not around the equivalence point in the reaction. So it's very important for you to choose the indicator for your reaction carefully. Let us do a quick comparison of our weak acid strong base titration curve to our weak base strong acid titration curve. So in this case, our weak base would be the titrand, which means that in the initial solution, initially in the flask, we're going to have a pH that is greater than 7 because we have a weak base. So in this case, we have ammonia being titrated against hydrochloric acid. So initial pH is above 7, and then we're going to see a gradually decreasing portion in the buffer region until it gets to this steep fall in the pH around the equivalence point. What you'll notice too is that the pH at the equivalence point in this reaction is going to be less than 7, right? So it's going to be more acidic because at your equivalence point, all of your weak base would have reacted and produced its weak conjugate acid. Its conjugate acid would hydrolyze in water to produce hydronium ions, causing the solution to be more acidic. After that, once you continue to slowly to add strong acid, the pH is going to continue to slowly decrease. So you'll notice that the bottom portion of your titration curve is going to look a lot more similar to your strong base, strong acid titration curve, but the initial part of your curve is going to have a lot more differences. Now, a couple other things to note or if we remember the half neutralization point, it also applies to your weak base strong acid titration. At the half neutralization point, which in this case is going to end up, the pH is going to be at 9.25. The concentration of ammonia and its conjugate acid are going to be equal in the solution, and then the pH is going to be equal to the pKa of the ammonium ion. So for a weak base with a strong acid, we'll have a similar approach to the pH calculation as our weak acid strong base. As the base becomes weaker and its concentration gets smaller, we're going to see that the pH change is going to be more gradual. And indicators that change in acidic pH are needed for your weak base strong acid titration. So if you look at the example before, phenolphthalein would not be an ideal indicator for your weak base strong acid titration of ammonia with HCl, but methyl orange would be more appropriate for that titration. So just quickly going over some strategies for when you're doing your pH calculations. At any point in the titration, the pH can be calculated if you know the relevant pKa's or pKb's, and if you have the concentrations of the acids and bases and their conjugates. Now, alternately, you can measure the pH, and if you know the concentrations, then you can figure out what the Ka or Kb of your acid or base will be. Now, the concentrations are either known from the concentration of your standard acid or base, or it can be calculated from experimentally determined equivalence volumes. If you are monitoring the pH of your solution during your acid-base titration, not only can you determine the concentration of the titrant if it's unknown, but you can also use this to determine what the pKa or pKb of a weak acid or base will be. And finally, if the pKa or pKb are known, then the pH. So you can make some calculations about the expected pH at different points in your titration, like we did in our examples, and you can compare this to measured values using a pH electrode to give some information about how accurate those measurements are. So just a quick summary for you to take a look at here. Just some a summary about some important notes about your neutralization titrations and titration curves. And just want to finish off with a look at the weak acid, weak base titration curves. So with your weak acid, weak base titration, it's much more difficult to determine what the endpoint or the equivalence point of your reaction would be. The steepest point, typically we look at the steepest point in the curve to find our equivalence point, but it's much harder to identify because the pH is not changing as rapidly for your weak acid or weak base. So you see there's not a steep change in the pH at the equivalence point as you would see for other titrations. Now, Of course, another way to track the pH is to use an indicator, but it's very difficult to find available indicators to accurately determine the endpoint for weak acid, weak base titrations. One strategy that can be used is graphing the derivative of the curve for a more accurate determination. And so by doing this, we plot the change in pH divided by the change in volume versus the volume of your titrant. And when we find the maximum value or the inflection point indicates the equivalence point of the titration. And this strategy is not only used for weak acid, weak base titrations, but it can be used for all the other titrations that we've discussed. Right? So that first derivative titration curve that we examined a second ago provides information to identify the regions of the curve which exhibit the largest change in pH per unit titrant volume, and this curve can be applied, as I said, to data from different types of acid-base titrations. Some additional resources if you want to find out some more information about titration, indicators, and do a quick little simulation to help you get more comfortable.